I'm going to tell you about visual search. And I wanted to work at the crossroads of search and deep learning. And images and deep learning works really well together. So what is visual search or image search? So that's Pinterest. I don't know if you're familiar with Pinterest, but you can share images and create like pinboards of different images. And they have this feature where you can select a particular area of an image, and then it's going to give you related images that are hosted on Pinterest as well. So they were the first one to introduce that, and it's a very popular feature on the platform. Bing also has an image search where when you search for images inside the image that are returned, you can select like a specific area, and then you're going to get related products. So can help them drive sales and drive revenue. It's a pretty big market, and there is this quote, which is, by 2020, more than half of all mobile searches will be voice or visual searches. So at Amazon, what we have is the visual search on mobile, but it's more right now geared towards product retrieval. So you look for exact matches. So it's not really inspired by. We just recently launched a product called Shop by Look, and that's closer to visual search, where you say which items you like, and it's going to try to match a blend of styles of the items you liked within a particular category. So for example, lamps or sofas. So how do we make this work? How can we find similar images? Well, it's a two-sided problem. So one is, how do we represent images? And then how do we efficiently search through this representation? So typically what we do is we first take the images and we put them through a lower representation. So we can use a neural networks that we stripe down of the last classification layer. So for example, the ResNet networks Tom was talking about. And then we use this lower dimensional representation. So people call it features or image embeddings or featurized representation, or we can see that as a fingerprint. And then we index that in an efficient data structure. So what I used in this example is it's called HNSW, Hierarchical Navigable Small World. And it's an algorithm that's actually, I did a bit more research recently. It's actually still the fastest right now. It has some drawbacks because it comes with extra memory footprint. But if you want to do fast k-nearest neighbor retrieval, it's actually the fastest one at the moment for data sets ranging in the few millions of items. If you want billion scale data set, you can look at the Facebook face package, which comes with a few different algorithms, including HNSW. So now we have indexed all these images. So we get a new image for a query. So we take it through the same network. So it's very important to use the same pre-trained network. Otherwise, the weights are going to be different, and you're not going to have the same featurized representation of your image. And then we do this k-nearest neighbor search. So just imagine that this image is projected into a lower dimensional space. In this case, it's 512 dimensions. And within this space of 512 dimensions, we find the k-nearest neighbors of this image. So why would this work? It's because your network learned to extract features of your images. So images that are similar would have these same features that have been extracted by your network that are then used to classify images in the right category. I'll touch a bit more about the impact of different training on different categories in terms of feature extraction afterwards. So we find these neighbors and then we return them. So I'll show you a quick demo. So I actually built a website where you can try out this system, and I provided the code as well. So if we take an image, for example, this dog over here, hopefully it still works, yes. So we see a bunch of related products. Actually, what's interesting here, you see, it's actually the same image that's been applied. Some artists just put it on a case. And as you move, you can, it's actually pretty fast because the entire operation is quite simple. So it's a forward pass on the network, and then the algorithm for retrieval is super efficient. So all in all, the actual processing is about 50 milliseconds. And you can see that it's pretty good at finding different things. One interesting thing, so for example, that's me doing some ice skating down in Robson Square, and you can find like similar jacket, but you can see how sensitive it is to some slight noise. As I'm moving, and for example, if I put my head here, you see how apparently I'm a rock star from the 80s. So I wanted to show a few maybe failure cases where it doesn't work that well, or actually just make you think about what is it actually finding. So here's a dress, and now we're looking for different dresses, but actually are we finding similar dresses, or are we finding similar poses of people? So you see here, it's all ladies like that. So if you wanted to do a real production-ready pipeline, you would need to think about domain-specific classifiers. You need to think about image segmentation. We saw at AMLC lots of papers actually introducing image object detection. I haven't seen yet one that did an actual image segmentation that was domain-specific. But for example, you could imagine that in a fashion domain, you want to segment the different piece of clothing. But if you add a human, let's say you're on a different domain that the human is just here, like using the tool, for example, you want to remove the human completely. So you cannot just use generic image segmentation. So that makes the entire pipeline a lot more complex. So that's it for the demo. I wanted to walk you quickly through the notebook. We still have a bit of time. So who is familiar with MXNet here? Okay. So I'm using the Gluon API here, which is like the more imperative API of MXNet. And I'll walk you quickly through the different steps. And you'll see the actual code to do it is super simple. Biggest part of this notebook is data downloading. So we use a data set from, actually it was made available to Stanford in 2013. It has 8 million images. And I downloaded 1 million of them, the latest 1 million, because the earliest images, it's actually only books. So not that interesting. I want also to show you, as I'm doing that, something quite cool that if you were there last week, Matthew Savory showed us the GPU monitor. And I'll show you how you can easily integrate in your notebook some monitoring code. So the first part was just downloading the image. I'll skip that. So we see here a few hyperparameters that are interesting. So the batch size, here we're not training, we're doing inference. We're trying to construct the index of all our images. So we're actually trying to use the biggest batch size that we can, because it has no effect on training. If your GPU can take it, then we should use it. Surprisingly here, as I'll show in a bit, the limitation is actually not the GPU, it's the CPU, because all these images come in different sizes, so I need to pre-process them, resize them, and that's actually what takes the most of the time. So the actual featurizer, if you want a featurizer from the Gluon model zoo, you only need these 2 lines. You first get a pre-trained model, and if we look here at if we split this cell, and we look at the net, you actually get the ResNet described by Tom. And you see that the output is actually set in a different block. So you have a first block, which is only the features, and another block, which is the output. So what we do, we just say, well, actually, our network is just the features. And that's it. That's your featurizer. Then you can pass in batches of images, and you'll get features back. You can hybridize this model as well, and you can export it. So the deployment, I did it using MXNet Model Server. So right now, very soon it's going to support Gluon models, but right now you need to export to the symbolic version, but you can do that with this 1 line. And then you get the symbol file and the parameter files. The data transform is pretty classic here, resizing, cropping, and adjusting. So each of these pre-trained model on the model zoo, they've been trained with ImageNet, which every image is normalized according to the mean of the data set and the standard deviation of the data set. So we apply that in order to get the best features we can. training loop, if we want to look at that, it's just here. We are logging every 100 milliseconds is calling the NVIDIA driver and asking for metrics, which is then sending to an InfluxDB, which is being read live from a Grafana dashboard, and I'll show you in a minute how it looks. So what we do, we just get the data from the data loader, put it in the GPU context, and then computing the features and storing that into a big map. So if I run it, and then I go to my dashboard here, you should see here, as I enter the context, so you might want to have it always running, but then your database is going to be filled up with useless metrics. So that's what I like in this one, when you can actually scope the monitoring to specific blocks of code. And you can see here I'm using around like 50% GPU utilization. And if I showed you my CPU utilization, and you would see I'm maxing out all my 32 cores. To create a search index is super simple. You can download HNSWlib. It's not a pip package, but you can compile it from source and then load it. And you say the maximum of elements and a few hyperparameters. So how this index works is it's based on a small world graphs. So you're trying to put next to each other images or features that are data points that are close to each other, and then you branch out to another cluster. And then it has an efficient traversal in order to give you, it's actually an approximate k nearest neighbor. So you don't actually get the nearest neighbors, you get, you can set a parameter to give you, it's a trade-off between speed and accuracy, basically. And yeah, this index that you build can be saved. And then when we do inference, like on the website, we actually load that into memory. That's how it's super fast. Okay, so if we look at our GPU, it's working well. And then you can do some random testing. So here was actually quite interesting to do that, to debug. So I just pick a random product, and it gives you the most similar. So I realize we have a lot of duplicates. You have a lot of products that are different but use the same images. So actually just that make me think that we could use that in some sort of like monitoring and quality control. So if we use that, we can actually find the same products. And it's probably used somewhere already, but I'm not aware of it. Okay, I'll jump back to the slides. So that was the notebook. It's available on GitHub. Feel free to try it and apply it to your own problems. So the data set, again, it's freely available. And how did I operationalize that on the website? So I wanted to touch quickly on the workflow I used. So first I worked mainly in Jupyter Lab, as you saw. On my GPU instance, when I was ready, I used a MXNet model server to package my web service into a container, upload it onto Docker Hub, or you can use the AWS registry as well. And then I started a task on the Elastic Container Service. So now, very recently, we introduced something called Fargate, which is entirely managed container deployment. So you don't need to have an instance onto which you deploy containers. You just say, I want to run a container. And then you say, I'll probably need like 6 gig of RAM and 2 CPUs or 10 CPUs, and you build according to that. So it makes it super easy when it works. And you get free auto-scaling and all the niceties, load balancing, and all that. So how it works, you get your HTTP request that comes in, featureization happens, you look up your items, and you send that back. And thank you.
All right. Wow.
Any questions?
For
Yeah.
the resizing part, I think the input image must be a certain size, right?
Yes.
You had both resize and crop, so
So
I think you just resize.
So what I do is I resize using the short edge. So let's say you have a rectangle, so short edge becomes 255, and then I center crop. If you just resize to like a square, then you're going to get deformed images, right? So I resize and then I crop. So I lose information, right?
There's dimensions appropriate, right?
Yeah, so yeah, first the smaller edge to the right dimension, and then I crop the square in the middle. So it's not ideal. Actually, you can use some convolutional neural network that are using adaptive pooling, it's called. So at the end, because convolutional neural networks, since they're sharing convolutional layer, they're sharing weight, so they're sliding across your image. You don't actually care. As long as you have like a minimum image size that you can get through your network, and because at some point your pooling is going to be too small, but otherwise you can put them as big as you want. The only issue is then you cannot have batches of these images, right? So you could, and using adaptive pooling at the end to reduce it to like 512, for example. So that's possible. The only issue, like I said, is you might need to group images into similar sizes, and then you resize them so that you can put them in batches so you can efficiently process them. It's possible, but I didn't want, for this example, I didn't want to do that.